Today we're going to go more into polynomials. Particularly, we're going to talk about polynomial division, and we're also going to talk about the rational root test. So let's start with polynomial division. So polynomial division is the method that we use to divide one polynomial by another polynomial. So just like with regular long division, that's how we can divide one number by another. With polynomial long division, we can use that to divide one polynomial by another polynomial. So here's our first example. X to the fourth minus 3x cubed plus 2x minus 5, all divided by x squared minus x plus 1. So we're going to start by setting up our long division problem. And when you set it up, you want to make sure that all of the degrees have been accounted for. So you'll see here that I've put a 0 in front of x squared because there was no x squared term there, but we want to account for it. So if we start with x to the fourth, then we go down to x cubed, then the next term should be x squared, and then x, and then the constant. So now to go through the long division, you're going to look at the first term, x to the fourth, and then the first term in the divisor, x squared, and you're going to ask yourself, what do I have to multiply x squared by in order to get x to the fourth? In this case, that would be x squared. So we're going to write x squared right on top of the x to the fourth. And now I'm going to multiply x squared by the entire divisor. So x squared times x squared times negative x squared times 1. So that would be x to the fourth minus x cubed plus x squared. Now I'm going to subtract this entire thing. That means that all of these signs need to change. So this is going to become minus x to the fourth plus x cubed and minus x squared. Now we are going to actually do this fraction. Well, we've already applied the minus sign to everything there, so we can just combine terms. So now we have negative 2x cubed minus x squared, and then we're going to bring down the 2x. And now we repeat the process again. So now you ask yourself, what do I have to multiply x squared by in order to get negative 2x cubed? That's going to be negative 2x. And then we multiply everything by negative 2x. So this will be negative 2x cubed plus 2x minus 2x. All right, now again we're going to subtract. So change all those signs and then combine. So now we have a negative 3x squared plus 4x, and we'll bring down the minus 5. Repeat the process one more time. So what times x squared will give us negative 3x squared? That's going to be negative 3. Let's multiply again. So we have negative 3x squared plus 3x minus 3. We're going to subtract, so we're going to change all those signs and then combine. So 4x minus 3x, that's x minus 2. There's nothing else left to bring down, and you'll notice that the degree here, x to the first, is smaller than the degree of the divisor, which is x squared. So our quotient is x squared minus 2x minus 3. And then for this remainder, we're going to put that over the divisor. So plus x minus 2 over x squared minus x plus 1. And that is our answer. Now there's another type of division that's called polynomial synthetic division. And polynomial synthetic division is what we call the shorthand method of dividing a polynomial by a linear factor with a leading coefficient of a equals 1. Now you'll notice in the example that we just did, we were not dividing by a linear factor, we were dividing by a quadratic factor. So we wouldn't have been able to use this shorthand method. So this shorthand method only works if you're dividing by a polynomial that's a linear factor, so x to the first, with a leading coefficient of 1, so it's not going to be like 2x minus 1, for example. would have to be dividing by x plus 3, x minus 2, x plus 7. Any of those would be fine. Let's do an example. So we have x to the fourth minus 10x squared minus 2x plus 45 divided by x plus 3. So we're dividing here by a linear factor, right? It's x to the first, and the leading coefficient is 1, right? That's a 1 in front of the x. Okay, so how we set this up, we start with the linear factor, and we take the opposite of that number there. So instead of x plus 3, we take negative 3, and we're going to write it in the box over here on the left. Then for the rest of the numbers that we write down, we are going to write down the coefficients of the dividend. So x to the fourth minus 10x squared minus 2x plus 45. And then we're going to put zeros in for placeholders anywhere that we seem to have skipped one of the degrees. So 1, x to the fourth. We're missing x cubed, so we'll put a 0 in for x cubed. Negative 10 in front of x squared. And then negative 2. And then 45. Now let's go ahead and go through the process. So I'm going to draw a line down here. The first thing you're going to do is you're going to take that 1 and you're going to bring it down. After you've done that, then for the rest of the process, you're going to multiply and add. Multiply and add. So 1 times negative 3 is negative 3. We're going to add 0 plus negative 3 is negative 3. Multiply again, negative 3 times negative 3 is positive 9. Add, so negative 10 plus 9, that's negative 1. Negative 1 times negative 3 is positive 3. And then add those together, we get positive 1. 1 times negative 3 is negative 3. And add those together, we have 42. Now, we're not quite done yet. Remember, this is just the shorthand method. So what we need to do is we need to convert this back into a polynomial. So we take our numbers here at the bottom, 1, negative 3, negative 1, 1. And what we're going to do is we're going to start with 1 degree less than what we started with. So we started with x to the fourth. Because we're dividing by a linear factor, x to the degree 1, we're going to go down by 1 degree. So x to the fourth was our first degree. So now, for our quotient, x to the third will be our first degree. So this will be 1 x cubed minus 3 x squared minus 1 x plus 1. And then the 42 that I've put in a little box there at the end, that's just to remind me that that's the remainder. So that's going to go over x plus 3. And there's our answer. Next, we're going to talk about the remainder and factor theorems. So the remainder theorem says that when dividing a polynomial, p of x, by a first degree polynomial, x minus c, the remainder is going to equal p of c. So that's a quick way to figure out what the remainder is without having to do the division. Now again, this only works when you're dividing by a first degree polynomial, x minus c. But all you need to do is you need to plug c into the original polynomial, and that will give you the remainder. Now the factor theorem is related to the remainder theorem. This says that when dividing a polynomial, p of x, by a first degree polynomial, x minus c, so same case, and when you do that and you get p of c is equal to 0, then you know that x minus c is a factor of p of x. Now really what you're saying here is just one step further from the remainder theorem. The remainder theorem says you plug c into your polynomial p of x and that gives you the remainder. The factor theorem says if when you do that and you get 0, that means the remainder is 0, then since the remainder is 0, you know it divides evenly, which means that x minus c must be a factor of p of x. Okay, let's take a look at example 3. Use the remainder and factor theorems to show that x plus 4 is a factor of f of x equals x cubed minus 28x minus 48. Okay, so we wanted, without having to do division, right, we're using the remainder and factor theorems to show that it is a factor. So we need to show that the remainder is equal to 0. So using the remainder theorem, we're going to plug in -4 into our polynomial f of x. So really we're finding f of -4. So plug -4 in. So -4 to the third gives us -64. And then minus 28 times -4, that will be plus 112 minus 48. And if we combine those, we end up getting that this is equal to 0. So that's all you need to do to show that this is in fact a factor, because you use the remainder theorem by plugging in -4, and because it's equal to 0, you can conclude that it is in fact a factor because the remainder is 0. So now talking about the rational root test. So the rational root test, this is the test that tells us that every rational root of a polynomial function with integer coefficients must meet the two following conditions. First, that the numerator is a factor of the constant term, and that the denominator is a factor of the leading coefficient. So what this means is that if you have a polynomial function and it has rational roots, all of those rational roots are going to be in the form where you can write it such that the numerator is a factor of the constant term and the denominator is a factor of the leading coefficient. Now, if you want to find all the rational roots of a polynomial, you would want to first list all the possible roots. So you would list all the different combinations of the numerator divided by the denominator, where the numerator is a factor of the constant term and the denominator is a factor of the leading coefficient. Now sometimes if the constant term or the leading coefficient are prime numbers, then there aren't that many possibilities to list out. But if either of those terms have many factors, then there will be a number of different combinations and a number of different possible roots. Now what you need to do is you need to check to see which of those actually work. So which of those are actually rational roots. So let's go through an example of this. Say you're given this polynomial function here, f of x equals 2x cubed plus 3x squared minus 8x plus 3. You want to look at the constant term and the leading coefficient. So the constant term, I'm going to write this in the numerator, and the leading coefficient, write it in the denominator. And I want to list out all the different possibilities of combinations that I can come up with that are factors of the numerator and factors of the denominator. So starting with the numerator, 3, what are all the different factors of 3? Well, 1 and 3, and also -1 and -3. So I'm going to write plus or minus 1 and plus or minus 3, and I'll do the same thing with the denominator. So for the denominator, plus or minus 1 and plus or minus 2 are all the factors of 2. Now we want to come up with ways, different possible ways to combine the numerator with the denominator. So for example, you can do plus or minus 1 in the numerator and plus or minus 1 in the denominator. You could also take the plus or minus 1 in the numerator and the plus or minus 1 in the and the plus or minus 2 in the denominator. Do the same thing with the 3, so plus or minus 3 over plus or minus 1, and then plus or minus 3 plus or minus 2 on the bottom. Now, depending on the problem that you have, sometimes you might actually come up with repeats after you've listed all these out. In this case, we don't have any, but say we had a plus or minus 3 over plus or minus 3, that would be effectively the same as plus or minus 1 over plus or minus 1. So let's just write these all these factors out. So we have 1, -1, 1/2, -1/2, 3, -3, and 3/2, and -3/2. Now you can check to see which of these are actually roots. So these are all the possible rational roots. So what this means is that if this polynomial has rational roots, all of them are somewhere on this list. But not all of these that are on the list are actually rational roots. So we have to determine which of these are actually roots. What does it mean that one of these is actually a root? It means that if you plug in one of these numbers in for x, and you were to simplify it, you would get that it's equal to 0. Right, so if you remember, a rational root is also known as a 0. Graphically, it means that it's an x-intercept, and x-intercepts have a value of y equal to 0. So if you plug in these values for x and you get y equals 0, that must mean it is a rational root. So I'm going to go ahead and take you through how we can easily do this on the calculator. So in your calculator, you want to plug in the function itself into your y equals. So into the y equals, I'm going to write 2x cubed plus 3x squared minus 8x plus 3. Okay, so once you have that into your y equals, what we're going to do is we're going to go over to our table. Now, if your table is already set up so that it auto-populates, in other words, it automatically has some values in there for x, well, what we're going to do is we are going to set up our table so that we can input our values of x. So we're going to click on second window, that's really to set the table set. And instead of auto for your independent variable, which is x, we want it to ask what the independent variable is. The dependent variable we're going to leave on auto so that it will automatically calculate the y value for us. Let's go back to the table. So now you see the table is empty, and now I can plug in any value for x. In particular, I want to plug in these values, these possible rational roots, and see which ones give me the value of 0 for y. Now you'll notice that we found that y is equal to 0 for 1, 1/2, and -3. So going back to our problem here, we found 1, 1/2, and -3 gave us a rational root of 0. Now we actually could have stopped at -3 and not have checked 3/2 and -3/2. Why? Well, if you look back at the original polynomial, that polynomial was degree 3. That means it has a total of 3 roots. So since we already found all 3 roots, 1, 1/2, and -3, we actually didn't need to see whether or not 3/2 or -3/2 would also be roots, because we know that they won't be. Because otherwise, it would have been a degree that's higher than 3, and because this is degree 3, we know we're all set. Okay, now what about finding all roots? What about roots that aren't rational roots? Well, the way that we find all roots is we always first apply the rational root theorem and any other given information to find as many roots as possible. So sometimes in a problem you might be told that a certain value is a root along with whatever rational roots you might find. So you'll use that to help. And then, after you found all the roots that you can from that, then you will use synthetic division to divide out the known roots and solve the remaining equation. So we'll do an example of this so we can get used to how this might work. So example 5, find all roots of f of x equals 2x to the 4th plus x cubed minus 17x squared minus 4x plus 6. So we start with the rational root theorem. We're not told any information about the roots. Start with the rational root theorem. So we take the 6 and the 2, the constant, and the leading coefficient, And we're going to write out all the different factors of the constant and the leading coefficient. So for 6, that would be plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 6. And then on the bottom, that's going to be plus or minus 1 and plus or minus 2. And now we come up with all the different combinations that we can. So plus or minus 1 over 1, plus or minus 1 over 2, plus or minus 2 over 1, plus or minus 2 over 2, plus or minus 3 over 1, plus or minus 3 over 2, plus or minus 6 over 1, and plus or minus 6 over 2. Now, there are a couple things to notice before we start plugging these numbers right into the calculator. And that's, if you look at this list that we came up with, plus or minus 1 over 1 and plus or minus 2 over 2 are really the same thing. So I'm going to cross this off just because it's really a repeat. Same with plus or minus 3 over 1 and plus or minus 6 over 2. So I'm going to cross off the plus or minus 6 over 2. So now we have this list, and I'm going to write it out. So this is 1 and negative 1, 1 half and negative 1 half, 2 and negative 2, 3 and negative 3, 3 halves and negative 3 halves, and 6 and negative 6. And now we're going to go through and find all the rational roots. So these are just all the possibilities. Now we want to find which ones are actually roots, which ones actually give you y equals 0. So you can easily plug in each of these into your polynomial just the same way that we did on the calculator. You can also just manually put them in as well if you'd like. But you will end up finding that there are 2 rational roots, 1 half and negative 3. Now, because we only found 2 roots, and looking back at the polynomial, this was a polynomial of degree 4, we know that there must be 2 more roots. Okay, so if we haven't found all the roots yet, now this is where we're going to use synthetic division. So we're going to continue on this slide here, and we're going to set up the synthetic division. Now, we did find 2 roots, right, at 1 half and at negative 3. Now, it doesn't matter which root you start with to do the synthetic division. You will get something different for the first step, but once you do the second step, you'll have the same thing. So let's say I start with the 1 half. And then I'll write out 2, 1, negative 17, negative 4, and positive 6. We'll do the synthetic division. So remember, this starts off by bringing the 2 down, and then we multiply, add, multiply, add, multiply, add. So 2 times 1 half is 1, and that together we get 2. Multiply that by 1 half, we get positive 1. Add that together, we get negative 16. Multiply that by 1 half, and that's negative 8. Add those together, we get negative 12. Multiply by a half, that's negative 6. And add that together, we get 0. Now we should expect to get 0 at the end. Why? Because 1 half is a rational root, and anytime something is a root, that should give us a remainder of 0, because it's a factor, it divides evenly. Okay, so now we still have 1 more root that we had found, negative 3, and I'm going to do synthetic division again. But this time, instead of doing synthetic division on the original polynomial, I'm going to do the division on this quotient that we just got, the 2, 2, negative 16, negative 12. So I'm going to go ahead and write the negative 3 right next to the 2 over here. And I'll do the synthetic division again. Really what we're doing is we're dividing out the roots that we know, we're dividing out those factors, and we're really simplifying this down so that we can work with what's left. So let's do synthetic division again. So we bring the 2 down. 2 times negative 3 is negative 6. Add that, we get negative 4. Multiply, we get positive 12. Add that, we get negative 4. Multiply that, we get positive 12. Add that, we get 0. And again, we should expect to get 0 here because negative 3 is a root. And when something is a root, that means that when you divide out that x plus 3, you should expect, because it is a factor, that the remainder should be 0. Now, what does this leave us with in terms of a polynomial? Well, we did synthetic division twice, so our quotient here should now be down 2 degrees. So this is going to be 2 x squared minus 4x minus 4 equals 0. Now I can actually simplify this down if I divide everything by 2. And I'm left with x squared minus 2x minus 2 equals 0. And now I need to find the rest of the roots. Now, you can check to see whether it's factorable, because that might be what you naturally start thinking. But since we've already found all the rational roots, we know that whatever roots are left are going to be irrational roots. So it is very unlikely, unless you maybe forgot a root or maybe incorrectly inputted something, it is very unlikely that this will be, if you've done everything up to this point correctly, this won't be factorable. So we're going to go ahead and apply the quadratic formula. So this is x equals positive 2 plus or minus the square root of 4 minus 4 times 1 times negative 2 all over 2. So now we have 4 minus 4 times 1 times negative 2, so that's 4 plus 8, so that's 2 plus or minus the square root of 12 over 2. And now square root of 12, we can actually simplify that. We can take out the square root of 4, which is 2. So this is 2 plus or minus 2 root 3 over 2. And then we can actually divide everything by 2. So this ends up being 1 plus or minus the square root of 3. So we actually found both of the remaining roots, right? 1 plus root 3 and 1 minus root 3. So all the roots are 1/2, negative 3. Those are the rational roots. And then the irrational roots are 1 plus root 3 and 1 minus root 3. And that's all 4 roots for this polynomial.